In today's video, we're going to be continuing our case study about the Arctic tundra, but this time looking at the carbon cycle. This is for the OCR A-level geography spec, where we will look at the carbon cycle specifically for the Arctic tundra for the Earth Life Support Systems bit of the specification. I've highlighted all the sections it's relevant to here. So when we talked about the water cycle, we talked about the fact that it had very low temperatures, and we talked about the idea that there is not much liquid water for most of the year. Well, these physical factors are incredibly relevant to the carbon cycle. If we add in the fact that most of the tundra is on this large crystalline rock, igneous rock, we talked about Precambrian Canadian shield, there are very few nutrients that come from that because it doesn't break down. And so because of all these three conditions, we find that there is very limited photosynthesis and plant growth. These are incredibly poor conditions for that kind of growth, and therefore we're not getting any of that carbon dioxide from the atmosphere transferred into the biosphere. So we would say that the carbon cycle in the Arctic is quite slow. There's not many transfers between the stores, and we'll talk about the dominant stores later on. So similarly, in terms of the water cycle, the conditions mean it's a very slow processes going on here. In terms of flows and stores, there is a short summer period that is above that negative heat balance, which lasts about 3 months, where there is actually quite a lot of sunlight, and that's the growing season. So during that period, we would get lots of plant growth, but still, if we average that over the whole year, the net primary productivity is still very low. So 200 grams per metre squared a year, which is incredibly low for any biome. And that's largely because of what we said before, very poor conditions for photosynthesis and only a very short window in which there can actually be growth. So we do see seasonal differences between the amount of growth and therefore flows and changes in the store, but overall it's very limited in terms of the biomass in the biosphere. In terms of how much, the carbon store in the biomass is somewhere between 4 to 29 tonnes a hectacre, and you could obviously compare that with what's in the Amazon, which is considerably more. We talked about seasonal change, and there is a seasonal change. In the summer, it obviously does heat up, it gets above freezing, and during that period, in that short growing period, we will see any of the plants that do grow, they will drop their leaf litter, and that will eventually decompose and go into the soil. So we do see some carbon from the limited vegetation that is there being transferred from the plants, the leaf litter, into the soils. Microorganisms that are in that active layer, for example bacteria and other decomposers, they are more active because it's warmer, and therefore they will break down this litter and release some of the CO2 via respiration to the atmosphere. So we are seeing movement of carbon as the seasons change. However, as we said in the water cycle, when the active layer defrosts, there is lots of flooding and lots of these seasonal pools that you can see in this picture, and because of that we get waterlogged conditions, and decomposers actually need oxygen to be able to break down any of the organic matter around it, especially any organic matter that would be below the surface. So that decomposition and therefore respiration is very limited because of the increase in the water in this period. So even though we are getting a change as to the flows and stores, during this period the conditions are still very waterlogged, and therefore it limits the amount of CO2 that goes to the atmosphere. One of the most important carbon stores is the permafrost. We call this a carbon sink. And in terms of how much carbon it's actually got stored in it, it's over 1,600 gigatons. Why is so much carbon stored in the carbon sink? Well, it's full of dead organic matter, so dead animals and plants that has been there, frozen in that soil for thousands of years, potentially longer than that. And like we said, this permafrost is the layer which doesn't melt. It's permanently frozen throughout the year. Because of the low temperatures that are there for 9 months of the year, that organic matter is not going to thaw, it's not going to break down. So because of that, carbon is being trapped there for thousands and thousands of years. It stays in that layer. There's no decomposition of it. The carbon remains in the permafrost, is not released. So we get this whole kind of wedge of ice under the surface, which carbon is trapped in, old organic matter that's been there for years, and it never gets touched because the temperatures don't get low enough to thaw it. However, this could change in the future. This permafrost actually is a sink, but it could become a source of carbon. So as temperatures go up because of global greenhouse gases, we're going to get global temperature rise. When the temperatures rise, that layer that's permanently frozen will start to thaw. And when that starts to thaw, that will allow decomposers and microorganisms to be able to attack the organic matter that's in it and start to decay it. As that decomposes, as those microorganisms are working on that, they will release CO2 versus respiration, but also there's pockets of methane that are actually trapped in that layers of permafrost, and as soon as we try to heat that up, that methane will be released into the atmosphere. So as we get more CO2 and methane released into the atmosphere, we get an increase in greenhouse gases. So this becomes one of those feedback loops that once this starts going, it could cause a lot of problems in terms of global temperatures and the permanent removal of the permafrost. We talked about it being over 8 million kilometres in terms of how big it is. That's a significant amount of permafrost and carbon that could be released to the atmosphere. So we're not quite sure what's going to happen with the permafrost and the Arctic tundra. We could suggest that there's one way in which the climate change worsens, the active layer deepens, and therefore the permafrost melts. As we can see from the picture here, as it deepens, that organic matter decays, and then we get this atmospheric CO2. And it's particularly bad because the methane that's trapped in the permafrost is 4 times more damaging for climate change than CO2. So it's that release of methane from the permafrost that could be particularly very, very damaging. However, there is an argument that as the permafrost starts to melt and we get bigger temperatures, larger temperatures, therefore there will be more liquid water, and combined with the higher temperatures and the fact that we've got more liquid water, we'll actually get a lot more photosynthesis, and therefore we'll get more plant growth, which would actually extract carbon from the atmosphere and store it in the biosphere. However, at the moment, the best predictions that scientists have got are saying that plant growth would only offset 20% of that methane being released, and therefore eventually it looks like the Arctic would be a source of carbon, but this is quite hard to predict at the moment because it's a lot of modelling and it won't actually be able to measure it at the moment. So we can see that generally the carbon cycle is very slow in the Arctic. There is a seasonal change in terms of flows and stores, and it's largely because of those severe physical conditions, very low temperatures, very little liquid water, but also the fact there's very little nutrients from the geology. Lots of the carbon is stored in the permafrost, and only in the future might we see a change in this depending on what happens with climate change.